Hopefully you've had a chance to try this problem. I don't blame you if you stopped a little early. This is triprotic acid. And we have the pKa's given, so that gives us the equilibrium constants for each of those acid dissociation or acid ionization reactions. Um, and and so if we start with a 0.75 molar concentration, the goal of this problem is to show you that you can calculate the pH based on that first acidic hydrogen ionizing rather than calculating each of the subsequent steps, right? We're actually going to, sorry, I'll give the punchline at the beginning, like a good scientist. The pH is going to be the same even as we take into account each of the equilibrium steps. You know, this really speaks back to the common ion effect, right? That what is really going on here is that we already have a hydronium ion around, and so it's going to shift the equilibrium for each of the subsequent dissociation reactions towards the reactants and not give a very significant increase in our hydronium ion concentration. And so in the future, you can just do it based on the first one, unless it's something like sulfuric acid. But so that aside, this will prove that point. Also, this will give you great practice with ice tables and subsequent ice tables. So it might be worth doing at least the first two. All of this said, let's go ahead and show the solution to this problem. I'll walk through the whole thing. Do not feel obligated to watch the entire video once you get the point. So first we need to write the stepwise dissociation reactions for each of these acidic hydrogens on our citric acid. We have a picture here of citric acid, and I've highlighted in red each of the hydrogens that are going to be the most acidic. So we'll start with the first one. So we're going to write this out. It's kind of a long thing. I'm going to use the version of the chemical formula that puts the acidic hydrogens in front. So it's easier to track that where we're at if we've lost one hydrogen, two, or three. I'm going to do A and B together. Here's my first dissociation reaction. I lose a hydrogen from my citric acid, and it's going to take on a negative charge as a conjugate base. And my conjugate acid will be hydronium ion. I'm going to write out the K expression, the Ka1 for this as well. So here's my equilibrium expression. Here is the first dissociation step. So this is the first one. And this is there's going to be two more. There's going to be three total. I'm going to write those out and then restart recording so that way you can compare what you were able to do for your dissociation reactions and the expressions that you wrote for each of these dissociation or ionization steps. All right, here are each of my subsequent dissociation steps. So in each one, note that we see we have three acidic hydrogens in our first one, we lose one. And then we have two acidic hydrogens when we start with our second equation, we lose one of those. And then we only have one, and we lose that in our third. And so our equilibrium constants Ka1, Ka2, Ka3 are all representing the products divided by the reactants for that specific reaction. And so these are all right here, and you can compare them to your own. So the next step then to calculate the pH of this would be to then build an ice table based on this first step. So this pH of a 0.75 molar solution. So we'll use this first step to build an ice table and determine what our equilibrium constants are. Then we would use those equilibrium constants to become the initial of the equilibrium expression, or sorry, the ice table for the equilibrium reaction for the second step. And then use those equilibrium concentrations as the initial for a third. And so you can keep doing these subsequent ice tables where you populate the equilibrium for the first step into the initial for the second reaction that occurs. So let's set this up for the first one and walk through it. So I'll write out my equation and I'll build up my ice table, and then I'll restart the video. All right, so I know that my initial concentration of citric acid is 0.75 molar. I'm going to imply then that I have nothing of my product so far. And so I'm going to figure out where equilibrium lies and how much I have of my reactants and products. So I'm going to put a 0 for my initial concentrations for each of the two products. And because that's a 0, my Q will be 0. And so that means that no matter what, I know that to establish equilibrium, this reaction is going to proceed to form products. That means I'm going to subtract from the product side and subtract from the reactant side and add to the product side. So in my change row, what I'm going to do is take that 0.75 molar and subtract X. Now it's just 1X because I have a coefficient of 1 as we're looking at just the dissociation of one of these hydrogens. And then I'll add X to each of the following products that form. So then my equilibrium concentrations are going to be 0.75 minus X, X, and X. All right, so now I can plug this into my equilibrium expression, which I had written before. And I've been given some information about that Ka value. I've been told, let's kind of do this separately, that the pKa is equal to the pKa is equal to 3.13. So to find the Ka value, I'm going to take each side of my equation and to the power of 10, right? So remember this 3.13 is equal to the negative log of my Ka. So by just putting both sides of this equation as the exponent on the number 10, then the log and these 10 here cancel out. So Ka is equal 10 to the negative 3.13. And I will be able to just plug that into my calculator and I get a value that's 7.41 times 10 to the negative fourth. So I'm going to use that value then to solve for this idea of X here in my equilibrium for this first step. So I'll have 7.41 times 10 to the negative fourth is equal to X times X divided by 0.75 minus X. So I'm immediately seeing that I'm going to have a quadratic. I have an X squared value and I have something that's just X. So I'll need to use a quadratic equation for this. I can rearrange this algebraically and find that 0 is equal to X squared plus 7.41 times 10 to the negative 4X minus 0.00055. Or 5.55 times 10 to the negative fourth. Let's do that. All right, I'm going to plug this into a quadratic equation. Remember, we have A, B, and C. And so quadratic. When I do this, when I solve for the quadratic and plug everything in, I get two possible x's. One is 0.02319, and the other is negative 0.02393. So only my positive one is reasonable. I can't have a negative value, so it's going to be this one right here. Okay. And I can now plug that back into my equilibrium concentrations. And so that means that at equilibrium, I'm going to have a concentration of H3C6H5O7 that's equal to 0.75 minus 0.02319. I'm also going to have a concentration of H2C6H5O7 minus that is equal to 0.02319, which will also be equal to the concentration of my H3O plus. Now, the products are going to become part of the next ICE table for this problem. Because my next dissociation reaction has my H2C6H5O7 minus, that is going to react with water to lose another proton. And so I'm going to just take those two forward. But before I do that, I'm going to calculate the pH at this point so we can compare it to the pH after we do the next ICE table that takes into account the second ionization of a proton from citric acid. So just stopping here, if I calculate pH, it's going to be equal to the negative log of 0.02319. and it's going to equal a value of 1.634. So let's keep that in mind. And at this point, I'm going to tell you that no matter how detailed we are in our subsequent ice tables and take into account every little thing, we're still going to get the same pH. And so if I were trying to solve this problem on an exam or in a lab, I would stop here and say, great, I'm going to have a pH of 1.6. Fantastic. But it's worth seeing how to then do these subsequent ice tables because they come in handy all over the place. All right, so we have some new information. Let's go on to our second reaction. I'm going to build up my ice table and pull my information down. Okay, I've set up my ice table. And what I've done is I've taken the equilibrium concentration of my H2C6, H5O7, which was that 0.02319, and I've put it in as the initial concentration. And I've done the same for my H3O plus, which I have some of after my first dissociation reaction. But I don't have any of my second dissociation step, the HC6, H5O7, -2. And so because one of those products is 0, I know this reaction is going to form products to reach equilibrium. So I know I'm going to subtract from my reactants and add to my products. The other piece of information that I've been given is that pKa2, which is 4.76. So I've calculated the Ka value, and it double check, it should be smaller than the first one, right? It's harder to form that -2 charge than it was to form the -1 charge, and it is. It's 1.7 times 10 to the -5th. Our other one was on the order of 10 to the -4th, so that tracks. So with this, I can start my second ice table, and this is now hopefully solving the ice table gets hopefully familiar. The areas that become tricky are the, wait, what do I put in as my initial amounts, and which direction is equilibrium going? And so those seem to be kind of the areas that people struggle with the most, and so they should be ones to pay attention to. So I'm going to subtract X from my reactant side, and I'm going to add X to my product side. That's going to give me values of 0.02319 minus X, X, and 0.02319 plus X. All right, I'll set up my K expression now. So Ka2 is equal to 1.7 times 10 to the -5th, which will be equal to X times 0.02319 plus X divided by 0.02319 minus X. All right, so now I'm gonna, for the sake of this not being a 2-hour video, do some hand waving algebra where I'm gonna set this up so I have it set up to 0, and then it'll be equal to something that's x squared plus x plus c, so ABC. So I can plug into my quadratic. This is worth practicing, and I'll have detailed solutions online as well for you to double check your work against. But so what this is going to lead to is 0 is equal to, I'll write this out. So I'll let you solve for X. I'll have the detailed solutions online rather than show all the steps in this video. But you're going to make sure you use the quadratic and you find an X value that's 1.697 times 10 to the -5th. This then gets plugged back into these equilibrium expressions right here, and we get a value that's going to be equal to 1.697 times 10. And I'm just going to focus on my products because these are going to be part of my next equilibrium expression. And so I'm going to have values then for my HC6, H5O7, that is just X, so that'll be 1.697 times 10 to the -5th. And for my hydronium ion concentration, this is going to look like 0.023207 molar. Okay, so now I would use these values in my next ice table, and I'll show you how to set that up. And I won't solve I'll show you how to set it up, and I won't go into the algebraic detail again, but I'd like to first calculate the pH here, right? And so let's take this right here, and let's calculate our pH for our second step. So the pH is going to be equal to negative log of 0.02327 it's going to be equal to 1.634. It's the same value we had before, right? So we went through this whole second ice table. We did good work. We have the same pH. What do you think will happen in the third step? The pH isn't going to change, right? What we're doing is we're refining this value. We're adding hydronium ion concentration that's so small that it's basically a rounding error now because we don't have enough significant figures to really track it. And so it's not making a meaningful change in the acidity of this solution. Now, just for the sake of completeness, I'm going to show you how to set up the next piece. And again, detailed solutions for this whole problem with the algebra done is going to be available online. So my next one would be that third dissociation reaction. So I'm going to set this up and then restart the video. All right, I've set up the next ice table. And what we have here is our third acid ionization reaction. And again, one of our products is 0. So we know that our reaction is going to proceed to form products to reach equilibrium. But we have a lot of hydronium ion around, like a lot. So it's going to not actually create much of our products to reach that equilibrium. We just need some. And so it'll be really small change, but so we'll have minus X from our reactants and plus X on each side. And so we'll have equilibrium equilibrium concentrations that are equal to 1.697 times 10 to the negative fifth minus X. We'll have X and we'll have 0.023207 plus X. Now my pKa for this is 6.4. Oh, I wrote that wrong. Which is going to be equal to a Ka of 3.7 or 3.98 times 10 to the negative 7. So pretty small. So if you go through and solve this one as well, and again, solutions will be online written out. What you find is you end up with a hydronium ion concentration that changes so slightly, it's so many decimal places out, it ends up being equal to 0.0232070029. So the change that's really being affected here is that 29 at the very end. This is an insignificant change in the hydronium ion concentration. But if you plug that exact value into our pH equation, we see that we calculate a pH of, wait for it, 1.634. And so these subsequent steps are not necessary for calculating a reasonable pH. But hopefully you've seen the technique of doing these subsequent ice tables and now have proven this to yourself. So you're like, cool, I'm just going to roll with that first Ka and be all right.